Hey guys, um, I'm slowly coming back to the living. So anyway, let's resume where we left off. Okay, so this is modern physics. This is still the fall 2020, and this will be chapter 6, part 3. Okay, and it's going to be still discussing phase and group velocities. Okay, so you will recall last time we ended constructing a two sinusoidal wave, and so from that we got that the sum of two sinusoidal waves actually gave rise to a high frequency part and a low frequency part. Okay, and so the low frequency part was this broad envelope, right? This broad envelope with which had a wavelength of delta k, which was given by k2 minus k1. And if we would allow that to evolve in time, it would have an angular frequency of omega 2 minus omega 1. Now remember, right, omega 2 is approximately equal to omega 1, which means that this difference is very small. Okay, so that allowed us to discuss the velocity of the argument. Okay, the velocity of the argument. Okay, and we talked about that very early on, right? The velocity of the argument could be given as points of constant phase. Okay, and so from that we were able to determine a velocity of the envelope, which we called the group velocity. Okay, so what I didn't mention at the time, however, was if we were to look at the phase velocity. The phase velocity is the high frequency component, and so if one were to look at that, one would determine that would be omega 1 plus omega 2 over 2 divided by k1 plus k2 over 2, right? Recall that the phase velocity is omega over k, which in this particular case then would have been omega 1 plus omega 2 over 2. K is k1 plus k2 over 2. And if you go back to the sum of those two waves, you'll see that this is the high frequency component. Knowing that omega 1 is approximately equal to omega 2, and k1 then is approximately equal to k2, we get that the phase velocity of those two waves that comprise the composite wave are going to look something like 2 omega over 2 2k over 2, which is going to look like omega over k. So each of those waves in the composite are going to have a phase velocity which is approximately the same. Okay, and we'll call that v phase. Your book calls that v1. Okay, because again, omega 1 is approximately equal to omega 2, and likewise k1 is approximately equal to k2. So your book calls that omega 1. Okay, so so let's now let's go and look at a couple of characteristics of this composite wave. Okay, a couple of things are borne out. One is if I were to redraw that, this is x. All right, this is the envelope. Here's the envelope. Here's the high frequency makeup underneath the envelope. Okay. You'll notice that even though this wave exists, right, in both directions for infinity, you can well imagine that if we were to add a bunch of these waves together, we can begin to get localization. Okay, as a matter of fact, we can talk about this wave having some localization, delta x, in this direction. Okay, and as it turns out, and Cameron might be the one who might be familiar with this the most. There's a relationship. There's a relationship between the spread, so to speak, the spread of wavelengths, and the spatial spread of the resulting wave. Okay, so a spatial extent of the wave, and that relationship then is something, goes something like this. Right, so that the spread in wavelengths times the spread in the spatial extent is approximately equal to 1. It's reciprocal. Okay, so this is a reciprocal relationship, and it's the proof of this is beyond the scope of this course, but clearly you can see that delta k then would be equal to 1 over delta x. Delta x is 1 over delta k, which means as one would get larger, right, the other would get smaller, and vice versa, right? So as delta k would get larger, delta x would get smaller. Okay, so the greater the number of wave components, right, to the composite wave, so to speak, then the smaller we can make the spatial extent of that wave. Okay, so this reciprocal relationship actually is rather important. Okay, so I'm getting back to just one more little tidbit, getting back to the group, right, to the group velocity, which then was going to be equal to d omega. dk. And this is usually evaluated at some central K0 or some central wavelength. Okay, and we'll talk a little bit about that later. But there's a very nice relationship that that relates the wave and group velocities, right? So so the group velocity, which can be obtained in the following way, right? So omega is actually a function of k. So we actually can write the following, right? And if you look in your textbook, it would be the top of page 168. Okay, and so we have, right, that omega is going to be equal to k times the phase velocity, right, for a particular wave. And so so omega then actually is a function of k, right? And so we write it like this. And this is called a dispersion relationship. It's called a dispersion relationship. And so one then can get the group velocity, which is nothing more than the derivative of omega with respect to k, right? So that's going to be, right, that's going to be the derivative, right, the derivative with respect to k of omega as a function of k. And so then V group then is going to be the derivative, the function of k. This is going to be then k times the phase velocity. Using the product rule then, right, then this is going to be then the phase velocity. And again, this is going to be evaluated at some k naught, right, plus k times the change in the phase velocity with respect to k, and again, usually evaluated at some k naught, okay? And so this relationship is actually pretty important, and comes up in physics all the time, okay? When one is talking about wave phenomena. All right. So let's apply these. So let's apply these ideas to matter waves. Okay. So now imagine that we have an electron which is moving from left to right with some speed v. I'm going to call it v classical. Okay, so it's the classical velocity with which that object is moving from left to right. Okay, and so what we'd like to do now, according to de Broglie, he said that this object can actually be thought of having some wave behavior. Okay, and so if we imagine now that the electron is actually comprised of a wave packet. Okay, so this is going to be right? This will be a wave packet. So we're going to add up. So the bottom line here is, right, we're going to add up, right? We're going to add a bunch of waves, that sum. As a matter of fact, we can just get rid of this. So a bunch of waves that sum where the particle is, and cancel where the particle ain't. Okay. So one can imagine that we're going to add a bunch of waves that are going to constructively interfere, right, where the particle is, so that the spread of this particle, right, this delta x, right, kind of matches where the particle is. And out here, where the particle isn't, right, we'll get destructive interference, okay? And so we're going to form this wave packet that's going to add a bunch of waves, going to have constructive interference where the particle is, destructive interference where the particle isn't, okay? So now let's look at some of the notions that we just dealt with to see how this plays out. Now, clearly, right? Clearly, the group velocity, right, better be equal to the classical velocity of the particle. Okay, and what's going to happen here is that the phase velocities here are going to be a little sketchy, and you're going to see what I mean by that as we develop this. Okay, so that's de Broglie's notion, is that we're going to have a particle. Okay, we're going to form a wave packet that's going to have some wave properties. The waves that we use to make up this wave packet are going to have constructive interference where the particle is, right? Destructive interference where the particle ain't. Okay, all right. So let's begin to put some mathematics to this. Okay, so we know from our previous discussion that the group velocity, and I'm going to write this as a partial now. It's going to be d omega dk. Okay, and we know that E is equal to h bar omega. All right, we're going to assume now the de Broglie hypothesis, which is P is equal to h bar k. Okay, which means now that omega is equal to h over h bar. Okay, k is going to be equal to p over h bar. And so then this is going to be the change in E over h bar over the change in P over h bar. The h bars cancel, they're just constants. And we get that the group velocity is going to be the change in energy with respect to the linear momentum. All right. Now, classically, right? Classically, we can work with this, right? Because classically, we know that if this object is moving with no forces on it, okay, no forces, right? So it's just going in a straight line at constant velocity, v classical, okay, then we know that the energy is just all kinetic. And so it's going to be p squared over 2m, okay? And so from this, we can get that the group velocity then is going to be the change in E with respect to P, which is then going to be the change in P squared over 2M with respect to P, which is then going to be P over M, which again, classically then is going to be MV over M, which then is going to be equal to V. So this is going to be V classical. Okay, beautiful. All right, let's take another view with this. Right, let's work in the opposite direction. Right, so let's take another look. Okay, so remembering now that omega is equal to the energy over h bar, right? This is the Einstein-Planck relationship, which now, right, previously was only good for light waves, is now going to be good for matter waves, right? So we have the Einstein-Planck relationship. Change in omega with respect to k then is going to be equal to 1 over h bar. Change in E with respect to k. Okay, again using the Einstein-Planck relationship. And then classically we have E is equal to P squared over 2M. So then the change in omega with respect to k is going to be then 1 over h bar. It's going to be the change in P squared over 2M with respect to k, which is going to be 1 over h bar, is going to be 2 P over 2M change in P with respect to k. 2's cancel, okay? And that's now going to give us then that the change in omega with respect to k is going to be 1 over h bar, P over M, change in P with respect to k. But we already demonstrated from above that this is equal to V classical, all right, the classical velocity of the particle, okay? So the classical velocity of the particle then is going to be P over M. P over M's cancel from both sides. And I get that the change in P with respect to K is equal to H bar, or that P now is going to be equal to H bar K. And we retrieve the de Broglie hypothesis, okay? So P is equal to H bar K, P is equal to H over lambda, okay? So we're feeling comfortable about the de Broglie hypothesis, okay? So what about relativistically, right? So we've been handling this classically. What about relativistically, right? So let's see if that actually is consistent with what we've been talking about so far. So V group is going to be change in E with respect to P, okay, which then is going to be change with respect to P, E relativistic, okay, where E is the relativistic energy. And so we know what the relativistic energy is going to be equal to, right? We know that E squared is going to be P squared C squared plus M squared C to the fourth. And so then the relativistic energy then is going to be the square root of p squared c squared plus m squared c to the fourth. Okay. All right. So then that V group, right, using relativistic energy is going to be the change in E relativistic with respect to P. That's going to be then 1/2 P squared C squared plus M squared C to the fourth. It's the negative 1/2 times 2 P C squared. Okay. Now let's take a little detour after the next line here, right? So what we're going to have then is then that VG, the group speed, is going to be, after the 2's cancel, it's going to be P C squared over the square root of P squared C squared plus M squared C to the fourth, which then is going to be P C squared over E relativistic. Okay, beautiful. All right. Now for each of the waves, that comprise the wave packet, okay, for each of the waves that comprise the wave packet, we know that V phase is going to be equal to omega over k, right? This is for each matter wave, that comprises the wave packet. Okay, so then V phase then is going to be equal to E over P, again using the Einstein-Planck relationship and the de Broglie hypothesis. Right, that's going to be equal to H times F. That's going to be equal to H over lambda. That will be then lambda times F, which we know is perfectly valid for the phase velocity of a particular wave that exists forever, right? A perfect sinusoid that exists that exists forever. Okay. Let's look at this in terms of the relativistic, right? So this is going to be E relativistic over the momentum, right? Over the relativistic momentum. And that's going to be gamma mc squared, where remember m is the rest mass. And this is going to be gamma mv. Gammas cancel, rest mass cancel. That's going to be c squared over v. And what's surprising from this is that the speed of the particle cannot exceed the speed of light, which means that the phase velocity for the individual matter waves that comprise the wave packet are going to be greater than the speed of light. Okay? And that is a pretty amazing result. Now I want you to recall, right? I want you to recall that perfect sinusoids, right, carry no information. And consequently, can move with velocities greater than the speed of light. And that's a pretty remarkable conclusion. Okay. So let's look at this in another way, right? So let's look at this another way. And this is more akin to what's in your textbook. Okay. So the phase velocity then is going to be F times lambda, which then is going to be equal to E over P using the Einstein-Planck relationship and the de Broglie hypothesis, right? So remember that F then is going to be H over E over H. Okay. Lambda from P is equal to H over lambda. Lambda is going to be H over P. Okay. And so then we get that frequency times the wavelength is going to be E over H times H over P, which is E over P, okay? So then the phase velocity then is going to be equal to the square root of the relativistic energy, okay, which is going to be P squared C squared plus M squared C to the fourth over P. I'm going to bring the P into the radical. So this is going to be the square root of P squared C squared plus M squared C to the fourth over P squared over P squared. This then gives us that the phase speed now is going to be the square root of C squared plus M squared C to the fourth over P squared. I'll factor out a C squared. It's going to be 1 plus M squared C squared over P squared. The phase speed then is going to be equal to C times the square root of 1 plus M squared C squared over P squared. We're now invoking the de Broglie hypothesis, then the phase velocity for a particular wave in the wave group is going to be then 1 plus M squared C squared over H bar squared K squared. Okay. All right. And again, this is all positive, right? And that's going to mean that P is going to be greater than C as we got before. Okay. All right. Beautiful. Now let's go back. Let's recall, right? Let's recall this result. Right? Let's recall that result. And let's rewrite that down, right? So recall then that V group was now equal to P C squared over E. And this is the relativistic energy. As a matter of fact, it's the relativistic momentum as well. So let me rewrite this just to drive those points home. So then this is going to be P relativistic C squared over E relativistic. Okay. And remembering that V phase was equal to omega over K, which was equal to VE relativistic over P relativistic, which then is equal to C squared over V from previous result. This gives us that P relativistic over E. Relativistic then is going to be then V over C squared. And then we can take this and we can throw that into here. And we get that V group then is going to be V over C squared times C squared, which then is V. And then this is actually V classical, right? This is the velocity of the particle. Okay, beautiful. And I shouldn't say V classical then. It's just going to be the velocity of the particle. Okay, beautiful. So so that kind of gives us a segue now into matter waves. Okay, and using the de Broglie hypothesis. Looking at the textbook now, if we we're going to omit section 5.4, okay, but I'll pick this up in section 5.5. So I want you to read section 5.5, and that's going to take us pretty much to the end of the chapter. As a matter of fact, read 5.5 and 5.6. Okay, and then that will get us to section 5.7, which discusses wave particle duality, and we'll spend a little time discussing that in the next module or two, and then that will bring us to the end of chapter 6. Okay, so we're closing in on the end of chapter 6. Very good. I'll assign some problems and get you started thinking about stuff at the end of chapter 6. All right, guys. All right, take care. Have a good weekend. All right, bye.